In this video, we're solving our third example problem for Bernoulli differential equations. We're given this differential equation here. Now notice the dependent or independent variable is t this time. And the claim is that this is a Bernoulli differential equation. If the independent variable is t, the standard form of a Bernoulli differential equation is the derivative of y with respect to t plus p of t times y equals f of t times y to some power, and that power can't be 0 or 1, otherwise it's linear. Now I'm comparing this to this, and if I can write this differential equation in this form, then I know it's a Bernoulli DE and it can be solved with the Bernoulli method. And before I go too much further, I just want to say that this is problem number 20 from section 2.5 from the Zill textbook. It's the 9th edition, and it's called A First Course in Differential Equations with Modeling Applications. So I'm looking at this and I'm trying to make it look like this. And I might think, yeah, this is Bernoulli, because if I distribute that 2t times y to this y to the third and the minus 1, I'm going to end up with 2t times y to the fourth. That looks kind of like this. And 2t times y times the negative 1, well, that's going to look like that. So with just a little bit of algebraic manipulation, I can make this look like this, and then we can solve this differential equation with the Bernoulli method. So let's rewrite that left-hand side, distribute on the right-hand side, add the exponents, and then to make this differential equation look like this, I need that y term on the other side. Okay, so now this almost looks like that. It's very close. Not quite, but it's very, very close. I've got a function of t times dy dt plus a function of t times y equals a function of t times y to the fourth. It's almost like that, but there's supposed to be a coefficient of 1 in front of dy dt, not this 3 plus 3 times the quantity 1 plus t squared. So we'll divide everything by 3 times 1 plus t squared here. And now this will be written in this form. So we have dy dt plus 2t over 3 times the quantity 1 plus t squared times y equals 2t times the quantity, or 2t divided by 3 times the quantity 1 plus t squared times y to the fourth. So this has this form. That's my p of t times y, and that's my f of t times y to the n, where n equals 4. So this is a Bernoulli differential equation with n equals 4. I'll call this dE star. That's that standard form that I want to start with. And now I want to come up with the appropriate substitution. So after you write the differential equation in standard form, so we write the dE in this form. It's a little too many, sorry about that. Form, there we go. Write the differential equation in this form. We identify n, and then we make the appropriate substitution. You're going to let u equal y to the 1 minus n. So we're going to let u equal y to the 1 minus 4. That's y to the negative 3. And then we're going to take the derivative of u with respect to the independent variable. So that's the derivative of u with respect to t. And remember, when you do that, you have to remember that y depends on t. Keep this here so we can still see it. All right. So if u is y to the negative 3, the derivative of u with respect to t is the derivative of y to the negative 3 with respect to t, which is negative 3, y to the negative 4. So you bring your power down, multiply by y to the 1 less power, times the derivative of the inside by the chain rule, or you can think of that as implicit differentiation. So we compute this, And then what you want to do is you want to take this differential equation and you want to multiply it by this guy. Because when you do, the resulting differential equation will be a first-ordered linear differential equation in U, and we can solve that with an integrating factor. So we'll take dE star, we'll multiply it by -3 y to the -4. Just going to write it over here again. And I'm leaving space because I know I want to multiply every term by -3 times y to the -4. So we're multiplying that dE in standard form, dE star, by -3 y to the -4. Okay, and if we've done everything correctly, the y's on the end should reduce. Y to the 4th times y to the -4 is y to the 0, so those guys are gone. The 3's are also gone. These 3's reduce, and this, by design, that -3 y to the -4 times dy dt is du dt. So we multiply the differential equation by this piece, and then when we simplify, we want to write the differential equation entirely in terms of u. This piece is du dt. Over here, I've got a minus 2t over 1 plus t squared, and y to the -4 times y to the 1st is y to the -3, and y to the -3 is u. So this times this together makes u. And then over here on this side, the 3's reduced, the y to the 4th and the y to the -4th became a y to the 0, which is 1. And now we've got a -1 times 2t, all divided by 1 plus t squared. And that is linear in U, which is a very good sign. So our job now is just to solve this for U and then back substitute and solve for Y. Easy breezy. You just have to remember the method for solving first-order linear equations. And remember how that method works. I'm going to call this dE double star. What I want to do here is multiply by an integrating factor. So I want to multiply by just the right function. So the left-hand side of this is the derivative of U times the integrating factor. To find that integrating factor, we're going to follow Bernoulli's method. Bernoulli said, the thing you need to multiply by is as e to the integral of p of t power, where this is p of t. So we're going to find the integrating factor by doing the following, or compute the integrating factor. We identify p. You compute the antiderivative of p. And then the integrating factor is e to that power. Now, be very careful here. That minus is part of p of t. If you don't have the minus, you're going to get the wrong integrating factor and it won't actually work. So whatever that sign is, make sure you consider that when you're identifying p of t. So p of t is -2t divided by 1 plus t squared. I need to anti-differentiate that. Let u be the denominator. Then du is 2t dt. And I've got a -2t dt, so I'll multiply both sides by -1. Then if I want to write this integral in terms of u, -2t dt is -du. And I've got a u right there, so that's there. But remember, that's not just a 1 plus t squared as a factor, that's a 1 plus t squared in the denominator. So there's an implied 1 up there. And then we simplify this. That's the antiderivative of 1 over u, which is the negative natural log of the absolute value of u plus c. I'm going to choose c to equal 0 because we only need one integrating factor. We don't need a family of integrating factors. And if c equals 0, and u equals 1 plus t squared were right here. Now at this point, if you want to, you can simplify this further so you have a coefficient of 1 out front. We don't want that negative 1 out front. We can get a coefficient of 1 using the following property from algebra. If you have a constant times natural log of a, you can bring that inside and make that a power. That's the same as log of a to the n. So there's an implied 1 here. You can bring that inside and make it a power. Now, we don't actually need the absolute values because t squared is always positive except for when it's 0. And then we add 1 to it, and then this expression is always greater than or equal to 1. So since it's always positive, there's no need for an absolute value. So this is really natural log of 1 plus t squared to the negative 1. And the integrating factor is e to that power. And e and the logarithm undo each other because they're inverse functions. And now you've got 1 plus t squared to the negative 1 there. So we did all of that to find the integrating factor. We want to take the differential equation in this form, standard form for a linear dE and u, and we want to multiply everything by this 1 plus t squared to the negative 1 power. I'm taking dE double star, which looks like this, and I'm multiplying it by the IF. So I've got du dt, and I had a minus 2t, and then check this out, I've got a 1 plus t squared down here. I'm going to bring that up to the numerator. So it's going to be 1 plus t squared to the negative 1 times u equals negative 2t times 1 plus t squared to the negative 1 on the right-hand side. Now I want to take all of these, every single term, and I want to multiply both sides by my integrating factor, which is that 1 plus t squared to the negative 1. So this becomes watch this. After distribution, you're multiplying here and here. You've got 1 plus t squared to the negative 1 times du dt. And then you've got a negative 2t, and 1 plus t squared to the negative 1 times 1 plus t squared to the negative 1. You add the exponents, that's 1 plus t squared to the negative 2. And you do the same thing over here on the right-hand side. Okay, so we multiplied the differential equation by the integrating factor, and then if we've done everything correctly, this left-hand side should be the derivative with respect to the independent variable, which in this case is t, of u times our integrating factor, that 1 plus t squared to the negative 1 power. So we found the integrating factor, multiply dE double star by the IF, and again, if we've done everything correctly, the left-hand side is the derivative with respect to t of your dependent variable times the integrating factor. And so we've got this. Let's check it out and make sure it's true. This is a function of t times a function of t. If I'm going to take the derivative of a product, I have to use the product rule. So we take the derivative of the first, which gives me that, times the second. Good. And then we want the derivative of the second times the first. Well, the u is there. I just need to figure out what the derivative of this guy is. Well, when I'm taking the derivative of this guy, I've got to use the chain rule. So I would get negative 1 times this quantity to the negative 2 power times the derivative of the inside. And the derivative of the inside is 2t. So yes, by the chain rule, the derivative of this is this, and it checks out. Okay, we're 2 steps away from getting u by itself. On the outside, we're differentiating. To undo differentiation, we anti-differentiate. Then we just end up with u times the integrating factor on this side. And then on this side, we've got to do a u substitution. I will let u equal that expression that's inside those parentheses. Obviously, this is a different u from that u. Maybe I'll use a different letter. Let's use w. Call it a w substitution. Let's let w be 1 plus t squared. dw is 2t dt. And I've got a negative 2t dt, so let's multiply both sides of that by negative 1. And then we'll write the entire integral in terms of w. So this negative 2t dt is negative dw, so we can substitute that. And that's a w raised to the negative 2. So every single part is accounted for. This piece is negative dw. This piece is w to the negative 2. You're just replacing it. And then you look at this and you say to yourself, do I have a rule for that? And we do. It's just the power rule. We add 1 to the exponent, and then we divide by the new exponent. Dividing by negative 1 is the same as multiplying by negative 1. Negative times a negative makes that a positive. Don't forget your c. So we got a 1 over w plus c, and w is 1 plus t squared. All right, and all of that is equal to u times 1 over 1 plus t squared. Guess I should keep writing that down. Okay, now if I want to get u by itself, I can multiply both sides by 1 plus t squared. Don't forget to multiply that c by 1 plus t squared. A lot of students forget to do that. Those will reduce, and you end up with u equals, if you distribute, this times that's just going to give me a 1. And then we'll have the c times the quantity 1 plus t squared. So we anti-differentiated both sides, and we just solved for u by dividing by the integrating factor or multiplying by the reciprocal there. Same thing. Okay, now remember, the whole goal of this, the whole purpose of this u substitution was to enable us to solve this differential equation from way back when. That was the differential equation that we started with. So I'm looking for a function y that satisfies this equation. The question is, how can I find it? Well, it turned out that if we made a substitution, the differential equation became linear in u. We solved the linear equation in u. And the last thing we need to do is back substitute. I'm trying to get back to y. Remember what u was in terms of y? U was y to the negative 3 in the original problem. Or in the original substitution, excuse me. So let's replace u with y to the negative 3. So you're going to raise both sides to the negative 1/3 power. And then you're going to have y of t equals all of that to the negative 1/3. You solve for y by raising both sides to the reciprocal power of whatever power is there. Now we were not given an initial condition, so this would appear to be a family of solutions. It was a nonlinear differential equation, so there are no guarantees that this is the general solution. Let's look through our method and see if there are any t values that we need to exclude. Okay, starting from the very beginning. I did divide by 1 plus t squared, but that's never 0, so I don't have to worry about that. We've got a y cubed in the denominator here, so y can't be 0. And it looks like no matter what we choose for c, y is not 0. Well, oh, it's never 0, but we can talk about why that's true in a second. Y can't be 0. And then let's see, what did we do on the next page? Y can't be 0 again. 1 plus t squared can't be 0 and it never is. U can't be 0, but that's 1 plus t squared. Again, same thing. Okay, so the only issues are the 1 plus t squared in the denominator and that y in the denominator. And let's look at this a little bit more carefully. A negative 1/3 power is the same as 1 over the cube root of that quantity. This function is never allowed to be 0. Is it ever going to be 0? I don't think it is, because it does not matter what I make c equal to. It doesn't matter what this denominator is. 1 divided by something is never going to be nothing. I'm never going to get 0 out of this. So I don't have to worry about dividing by 0 when y is equal to 0. There's no restriction on the values of t or c there. So yeah, let's look at this, but we also can't have a 0 in the denominator here. So c times 1 plus t squared is not allowed to equal 1. Or yeah, c times 1 plus t squared is not allowed to equal -1. I'm trying to think, is there any value of t that would ever give us a -1 there? Well, if we're trying to have a restriction on t, I guess we'd have t squared plus 1 is not allowed to be -1 over c, and t squared is not allowed to be -1 over c minus 1. And you might say, well, that's always negative, isn't it? So it's never going to be equal to t squared. But not necessarily. It depends on the value of c, doesn't it? If that c is negative, and it's, you know, there are values of c where this could lead to an issue, a problem. But t can't equal plus or minus the square root of this. So the domain is going to be, or the maximal interval of existence would be, it's going to depend on the initial conditions, of course, but that denominator can't be 0. So what I would do if I had some initial conditions is I would use the initial condition to find the value of c. And then once I have that value of c, I can use this relationship to define the maximal interval of existence. There are lots of different cases here. I'm not going to go through all of them. So we'll just state this family of solutions and be done. We usually like to state the maximal interval of existence as well, but that's okay, not this time. So we got y by itself, and we have a family of solutions to the differential equation. Now, if you're asking yourself, what is this? What is this function? If you take its derivative, and you substitute it in over here, and you replace y with that function, and you replace y with that function here, and simplify, the left-hand side is going to equal the right-hand side. So this is a function that you can take the derivative of and substitute it in here, and it will make the equation true.